Well, can you believe it? We are almost finished. We've got two sections in Chapter 11 to cover and just one in Chapter 12. So let's get to it. Section 11.1 is called the Goodness of Fit Test, and basically means that somebody is going to make a claim and then we have to see how well, or the word goodness, how well the data actually fits. So in the past, we could make claims about one proportion or even two proportions back in chapters 8 and 9. So for example, test the claim 14% of Americans approve of the job Congress is doing. Someone makes a claim like that, it's just one proportion. So there's the claim, P equals 0.14. But what if it was more than one or two proportions? So for example, the students at Hartnell College. Somebody says 62% are Latino, 24% are Caucasian, 5% are African American. So then we've got three claims. P1 equals 0.62, P2 is 0.24, P3 is a 0.05. So how can we do that all at once rather than having to do three hypothesis tests? Well, that's what the goodness of fit test does. So we're basically trying to see how well the data fits those percentages. But first, a little bit of new notation. So a capital O stands for the observed values. So you actually went out to Hartnell and talked to people and saw or asked them what ethnic group they would put themselves in. Expected is basically coming from those percentages. K is the number of categories. In that last example, it would have had 3 categories. And then N is how many people you actually talk to, or the sample size. So we're going to be using this idea that the mean is N times P. So if someone makes a claim for the proportion P, we would just multiply N, how many people there are, times that P. And those are going to be called the expected values. And we'll need to do that for each category. It goes fast. It's just the N times the decimal, the N times the decimal, and the N times the decimal. Then the test statistic. So this says for each category, take the observed minus the expected, and then square it. And then you divide by the expected, and you add that up for each category, and that is going to be a chi-squared test. Since it's chi-squared, the critical values are in table A4. And for degrees of freedom here, we use K minus 1. Number of categories minus 1. And these are right-tailed test only. So if we're going to be using 95% confidence, then over in the right tail, we would use 0.05. So here's an example. Test the claim that student tardies are the same proportion each day of the week. So here's the observed tardies. So this was over a period of time. So Monday actually had the most tardies, people coming in late. Tuesday was actually the least. So test the claim that these have the same proportion. Well, if you add up these numbers, 16 plus 8 plus 10 plus 11 plus 15, that equals 60. So a total of 60 tardies. And then because it's Monday through Friday, there's 5 categories. K equals 5. Now because my claim was that they're the same, basically I'm saying these 60 should be divided amongst the 5 categories evenly. So if you do 60 divided by 5, you'll get 12 for each one. So if my claim was true, then all of these should be 12s. The next thing is do that formula. So it's just going to be 16 minus 12 gets squared divided by 12. And then 8 minus 12 gets squared divided by 12. Look at my fancy arrows right there. And when you type that into a calculator, and there's not really a faster way to do it other than just type it in a calculator, then the test statistic turns out to be a 3.833. Okay, now I should write down the information. So since they're all going to be the same, if you take 100% and divide by 5 days in a week, it's going to be 20% on Monday, 20% on Tuesday, 20% on Wednesday, etc. 20% for each day of the week, Monday through Friday. Then make a nice chi-squared distribution starting at 0. And the number of categories is 5. So the degrees of freedom will be 5 minus 1 or 4. And I'm using 95% level of confidence, so this is going to be alpha equals 0.05 in the right tail. Then get you a table A4, and we're only going to be using the right side over here. So this is a 0.5, so use this column, and then go down to where degrees of freedom is 4, and the magic rectangle says the critical value is 9.44. There we go. 9.44. Now when I did that formula on the previous page, it turned out to be the test statistic is 3.833, and that lands right about here, which means we cannot reject. So in fact, we cannot prove anything in this particular case. Then for another example, test the claim that in Monterey County, 67% of people drive, that should say drive, I guess drive, ride, whatever. They go to work in a car all by themselves. 17% carpool, and 2% take public transportation. So a group of 30 people were asked how they get to work. And 22 of them said they drive alone, 6 said carpool, and 2 said they take the bus. So when you add these up, that's of course 30 people, and there's 3 categories: alone, carpool, or bus. So K equals 3. So then take each one of these percentages, 0.67 for the 67%, so 0.67 times the n, so this is the p times n, that one equals to 20.1. Then the next one is 17%, so that's 0.17 times 30. Oops, I forgot my equals sign. That's supposed to say equals 5.1. And then the last one is 2%, so that's going to be 0.02 times 30 is a 0.6. And if you look, these numbers, they're not too bad. They're sort of close to each other. So what's going to happen? So again, it's going to be the observed minus the expected, square that, and then divide by the expected. Hey, where's my fancy arrows? Oh, there they are. So the 5.1 goes right there, the 0.6 goes right there, and again, just type that into a calculator and get 3.605. So here's my table, and since K equals 3, that means degrees of freedom equals 2, and just like with the last one, it's going to be 0.05 for the right tail. So the critical value is 5.991. And the 3.605 would land right about here, and since it does not go past 5.991, that means failed to reject, or in other words, we did not prove anything. Desafortunadamente. Okay, see you again soon.